Okay, so our speaker just left. He had to go out, so I'm telling jokes for the rest of the time. Nobody's jumping up and say, "Oh boy, I can't wait." What they were doing is jumping up and say, "I'll see you later." Anyway, I want to introduce James D. Walker. He's works for Southwest Research. He's the director at Southwest Research Institute, and he has been, 35 years, I believe you told me earlier. That's amazing. Southwest Research, if you don't know anything about it, it is just a phenomenal place, and I know he's going to talk a little bit about that. He's an adjunct professor at the University of Texas. He's got 2 children, and earned his PhD at age 23. I can't even spell 23. Anyway, James, why don't you step up here? Thank you so much. And I told them that you're going to speak in English, not in professor stuff. Anyway.
Okay, well, thank you very much, and thank you, all of you, to the service you've done to our country. It's greatly appreciated. I'll talk today about some work we've done at Southwest Research related to the space program, and in particular the Space Shuttle program. But this is a couple pictures of Southwest Research Institute, which was founded in 1947 after a man named Tom Slick returned from service in World War II. He was in the Navy, and he was a, what do we call it, man of independent means. So he was looking for things to do. The family bought a ranch, which used to be outside of San Antonio and now is completely inside of San Antonio. So you can see a picture there in 1947 when the Institute began. There's a picture in 97, and then this is a picture today of what the Institute looks like. So we have about a little over 3,000 employees on a 1,500 acre campus. The red circle is the part that I work in. That's where our laboratories are for the impact physics group that I'm a part of, that I'm the director of. And we also, like this organization here, we're a 501c3, so we're a nonprofit science. For us, we're a research and scientific organization. This is a picture of Tom Slick when he signed the charter. He passed away in the 1960s in a plane crash. He was kind of a dynamic individual, and you can download some podcasts, which we're not related to at Southwest producing, but talking about his life and some of his adventures. And for example, he's famous in part for going on hunting expeditions. In fact, that's how he died, returning from a hunting expedition when the plane crashed. And also, he went to the Nepal area looking for the abominable snowman on one expedition, so he thought that was exciting. But his family made it big in oil. They used to live in Oklahoma. Because of the kidnapping, they relocated to San Antonio and remained pretty low profile. And he has a couple children who are still on the board, but he essentially got it set up, and then it was just kind of watched from a distance. I mean, he was president of Tesoro for a while, and he was still very much in the oil industry. And that's how Southwest really got started, was in the oil industry. There's still lots of engines, fuels, lubricants kind of work that goes on. Though John Cutchall and I, who helped arrange this visit, if you want to raise your hand, that's John, we're both in the mechanical engineering division. Okay, what I'm going to talk about today was paid for by you, the taxpayer, and the funding came through NASA and the Columbia Accident Investigation Board. I'll talk about the organization the aspect we were involved in. We realized when it came to the accident of the space shuttle, there were lots of people involved in the investigation, and you'll just see a little sliver of what was going on. So the Columbia accident, so STS, Space Transportation System 107, was the 113th flight of the Space Shuttle program, and it was the 28th flight of the Space Shuttle Columbia. It disintegrated Saturday morning on on re-entry February 1st, about 2 weeks after the launch, leading to the loss of all 7 crew members as well as the loss of the vehicle. And we even had some people from Southwest Research who were up in the Dallas area to film, take pictures of the re-entry of the vehicle because it happened that morning and it would be bright enough to see, and so they saw the debris coming down. If you're really interested in this topic, I highly recommend the Columbia Accident Investigation Board report. It's very well written. It's for the intelligent layperson. You can download it for free online. The part I'm going to talk about, we got a few sentences, essentially. I mean, that's what we got in the official report. What I'll be talking about is more in a technical appendix that I wrote on the impact. But it talks about the physical cause, which I'll mostly be talking about, how the accident happened. But then it also talks about an organizational cause. We had nothing to do with that, but I will mention something because many of you may be interested in some of the conclusions of the investigation in that fashion. And this is the appendix I wrote on the impact, the real physics. So if you want the equations and stuff, this you can also download for free and see what's going on. So the event happened because this orbiter is attached to the external fuel tanks, which hold liquid oxygen and liquid hydrogen, so they're very cold. And those external fuel tanks are covered with an insulating foam, whose intent is to prevent ice formation on the otherwise metallic fuel tanks. And so the big orange thing is this foam that's covering the metallic fuel tanks. The orbiter itself is attached to the bipod ramps, which are bipod connections at least, and those steel fittings are covered with bipod ramps of foam. And what happened during the ascent, when the space shuttle went up in mid-January, is that the left bipod ramp separated. At the time, the shuttle was going at about 1,600 miles an hour. The shuttle was at 66,000 feet. And that piece of foam took, as you can see, less than 1/5 of a second to travel the distance between where it left the bipod connection to where it impacted the left wing, the leading edge of the left wing of the space shuttle. And that's what led to the accident. When we lost the vehicle, there were lots of theories about what might happen. We got a call Monday morning. As I said, it happened Saturday morning. I was at work and saw a notice on it and talked to some other people at work. And it's like, whoa, this is not good. We weren't working on the shuttle at the time, but Monday morning we got a call from NASA asking, could our impact physics group assist in the investigation, since one of the proposed mechanisms of the loss was this impact of foam on the wing, which they were aware of, it happened. And then it even had a committee looking at it. So this is the best footage, which came out about 2 months after the loss of the vehicle. We're 2 months in the investigation, so you can see the piece of foam as it's coming off.
Oh, wow.
And part of the problem is it wasn't really clear on where the impact had happened. During re-entry, the very first anomalies started showing up in the landing gear area of the wing, where they started getting some anomalous readings coming down from telemetry. So the focus of the initial investigation was in looking at this under the wing part, which was a possible place where the foam might have struck. Now initially, Bush 2 gave us 60 days to answer the question. So it took 6 months, but everybody's in a rush to try to understand. So the focus was really on this underneath part of the space shuttle. And to give you a little comment about what happened, so to get to orbit, the space shuttle does a burn. It's now retired, but so it did a burn of about 8 minutes long, which gets it to a relative speed of 17,500 miles an hour. That's the speed relative to the ground to be in orbit, 17,500 miles an hour. So to slow down, to come back and land, you have to get rid of that speed, and the way it does is by frictional heating in the air. So as it comes down through the air, it's slowing down, and it's just like when you rub your hands together and they get hot. The same thing for the shuttle, it gets extremely hot. And for example, the leading edge panels, which are made out of a carbon-carbon composite, get to some 3,000 degrees, 2,900 degrees Fahrenheit, 3,000 degrees Fahrenheit. They get extremely hot. And you've also heard about the famous thermal tiles, right? And those aren't the leading edge, but that's the underside of the thermal tiles. So we were looking at an impact there. An important part in the success of the investigation was that this box was recovered about 2 months after the loss of the vehicle. Columbia was the very first space shuttle to fly into orbit and to come back. Because of that, it was the most extensively gauged of all the space shuttles, and there were strain gauges throughout the wings. And they were still collecting that data, though I don't think NASA was using it anymore. The interest was on the first few flights to make sure it was flying like expected, and the wing, wings flex, right? For those of you who fly, you know that, and for those of you who ride on airplanes, if you look outside, you see the wings flex, and the same thing happens with the space shuttle, right? So they wanted to know how they were flexing and to make sure everything was occurring correctly. This data was still being collected, and by looking at when gauges went offline during reentry, it was possible to rebuild the burn-through path on the wing when this quarter was recovered. Okay, so our first focus was the main landing gear area, in particular the door, which is covered with the thermal tiles. So those are thermal tiles that are put on the landing gear of the Enterprise, which was the first shuttle built, but it never went into orbit. It was just used for subsonic flight tests. And those are some other staff from NASA and Southwest. It was tiled. We have lots of guns. I'm in an impact physics group. We have lots of guns. And these are our slow guns, which only shoot around the speed of sound. They're just big, high pressure gas where then you just push the projectile. We have really cool stuff. Like we have a big gun that shoots at 6 kilometers per second, shoots big stuff. Like that's 15,000 miles an hour, right here in San Antonio, where we do kind of work related to orbital debris, and we're doing work that's related to hypersonic missile defense right now. So we're doing lots of stuff related to that. So this is a gun that we use primarily for launching foreign object debris, FOD, into aircraft structures. And also we use it for bird impacts on aircraft. So that's one thing we use it for. Yeah. So we launched foam. And here's a video, and we see the piece of foam coming in, striking the tiled surface there at approximately the angle we would expect. And you'll notice a couple things. One, the piece of foam doesn't break up, right? Which didn't look like the video we saw. There's actually minimal damage. The lines you see are mostly from the magic marker coloring we did for fiducials on the foam, right? So there's actually minimal damage to the surface. One of the first conclusions was that it wasn't an impact on the thermal tiles. This is what the thermal tiles look like on the left. They're a white sintered material that's covered with a black glass for the bottom tiles, which is black. There are also tiles on this top surface which are covered with a white glass. And that's for thermal emission when you're on orbit, so you can control the temperature. We took the materials because if you're going to do impact, you have to go beyond nice little flexing of materials and you have to crush them. So we crushed this is crushing the foam, this is crushing the thermal tiles. That allows us to build mathematical models so that we can start doing computations like this. Here's just a little cube hitting one tile, but then we increase it to the actual event. We looked at computations which said, okay, well now that we have a model, where's the region of damage and no damage based on impact speed and impact angle on the tiles? And I won't get into the details here, but it allowed us to then develop a theory. I had to show an equation, right? I mean, we had to have at least one real equation. This is non-trivial, but this next one's trivial, so that one doesn't count. But we're able to develop a simple theory, which is the line there going through the data points of calculation. So below that, we have no damage. Above that, we have damage. And so we had a good theory. We had good models. The question is, based on the ascent and where you could hit the thermal tiles, would we cause damage? And essentially, the answer was no. If you look at the circled region, that's where the Columbia foam strike happened. And so the first thing we did in the investigation, which did take the first 3 months, was show that the discussion about, hey, would a foam strike on the thermal tiles cause the accident? And the answer was no. So if it wasn't on the thermal tiles and it was still a foam strike, where might the accident, the strike have happened? And so then the focus became the leading edge panels, which are on the leading edge of the wing. So we took a structure, built a structure and put then real panels from the shuttles on there to see what would happen during impacts. This is a top view of the hardware that we took off Enterprise. Enterprise, as I told you, was the first one built, and it was on display at the I think it was on display at that point. It's certainly at the annex, at Dulles Airport, the Smithsonian annex they have for the planes. Now the one that's there is the Discovery, which, if you're keeping up with the news, our Texas senators are insistent that that's going to be moved to Houston instead of being left in Washington. We'll see what actually happens, right? But they're working on that. But this was from Enterprise, and we used to get, until we returned it after a few years, emails from the Smithsonian saying, "Where's our stuff?" We're like, you should be proud that your stuff got used for real things, right? So we, this is not what the inside, so these are the panels, the carbon panels, the one that get to almost 3,000 degrees during reentry. And it's just like it's just like a pot on the stove. You put a pot on the stove and we hold it with the handle because it's the pot. We don't pick it up by the pot because that gets hot. The same thing, these panels get extremely hot. And you'll see, and I guess I do have a little pointer here, but we only hold them by the corners because they get extremely hot. This isn't what it looks like when the shuttle flies because it has a foam in here that's covered with the Inconel foil to help prevent radiative transfer of heat from the underside of the panels onto the aluminum spar, which is what you're seeing here. But we didn't need that. That wasn't a structural component. And so we were able to put lots of additional gauging and cameras in there to see what happened in tests. So this is the setup. Even though it's bright sunny skies, we still have lights because we're using really high-speed cameras. So I understand you guys have a theater here, so this is a motion picture trivia test. How many frames per second do movie theaters show? Do you know? Anybody know? It's 24 frames per second. Actually, at 24, most of us would see a flicker. So what the cameras do, the projector, of course now everything's electronic, so now I'm going back to mechanical. But the mechanical projectors would show each frame twice, so that the apparent playback speed was actually 48 frames a second, and so you wouldn't see a flicker. But we're running cameras here at like 7,000 frames per second, more than 24, right? And so we need more light. So even though it's bright, sunny Texas, we needed even more light, so we have lights around there. We also, in our labs, we have cameras that can run at millions of frames a second. And often the illumination there is with pulsed lasers. We can get enough light to get images for the kind of images we take. We impacted RCC, reinforced carbon-carbon panel number 6 first. This one had flown 30 flights on Discovery. It had a crack in it, but the fueling was, that really isn't enough to cause the loss of the vehicle. But then panel number 8, so this was and there were lots of O's that day at the test because NASA had a lot of VIPs there to see this test. It happened in July, super hot day. But we showed that it was a plausible explanation that a foam strike on the reinforced carbon-carbon panel could put a hole in it, which was big enough to cause problems. So this panel in particular had been taken off Atlantis, which had flown 26 missions. You'll notice it's about 16 inches across the hole. The NASA Ames group that was doing reentry calculation studies estimated they think the actual hole was probably about 10 inches across that was on the leading edge panel. These are some high-speed videos at slow speed playback, so you can see what happens. You see the foam deforms and then the panel undergoes a structural failure. And then you can see it happening here, but this also agrees with the other footage I showed you, is here, because of the break, the foam actually gets caught and the foam is broken into pieces. So that agrees with the spray of foam that we saw in the other thing. So this is one view, this is another view, looking down onto it. You can see the big piece. Afterwards, hindsight is always more clear, or usually more clear. They looked at radar tapes of looking at the shuttle, and it looks like on day 2, after ascent that a piece floated away from the orbiter, and people think it might have been a piece from the panel afterwards, that it got caught in there during ascent, and then afterwards it kind of rattled and drifted away from the spacecraft. It's the kind of thing that's not noticed at the time, right? But now when you're like, oh, now let's start really paying attention. It's another view. This is the old way we used to do fiducials, to do measurements. It doesn't matter at this point because it all broke. But when we do measurements to do that, nowadays we just spray with speckle patterns, and we use 2 cameras with some obliquity to them, some parallax, and then we're able to exactly compute what the deformations of surfaces are and stuff. There's been lots of amazing advances in camera and optical metrology kind of work. And this is looking at, as it comes right towards you, you can see the piece of foam as it struck the thing. So this then became the plausible explanation. We also did calculations looking at what the stresses were like. And see, I think I have a video here so that you can see that the stresses build up in the panel, which then leads to a crack, which then leads to the failure of the panel. So when the stresses reach a critical state, because these panels, these reinforced carbon-carbon composites are fairly brittle, then it breaks. Okay, so what were some investigation conclusions we had? Well, the first one is a technical one. The second one, we have the modeling experiment showed that an impact on the underside of the wing was not the cause of the accident. So part I wanted to point that out. You'll often hear, oh, those thermal tiles. Well, it actually wasn't the thermal tiles that failed on the space shuttle. It was this carbon-carbon leading edge material. That's where the failure happened. So we showed with experiments and computations at Southwest Research, as our supporting NASA and also our supporting the Columbia Accident Investigation Board, that this was a plausible explanation. The forensics is what then led to it being the actual explanation, right? There's a difference between a plausible explanation versus an actual explanation. The reconstruction of the pieces, as well as the really critical information from the data recorder, is what led to the strong conclusion of what happened in this investigation. This was the conclusion of the Columbia Accident Investigation Board. The physical cause of the loss of Columbia and its crew was a breach in the thermal protection system on the leading edge of the left wing. The breach was initiated by a piece of insulating foam that separated from the left bipod ramp of the external tank and struck the wing in the vicinity of the lower half of reinforced carbon-carbon panel 8 at 81.9 seconds after launch. During re-entry, this breach in the thermal protection system allowed superheated air to penetrate the leading edge insulation and progressively melt the aluminum structure of the left wing, resulting in a weakening of the structure until increasing aerodynamic forces caused loss of control, failure of the wing, and breakup of the orbiter. So in mid-January, when the launch happened, and it was going about, you'll remember, 1,600 miles an hour, it's about 66,000 feet, this piece of foam breaks off the left bipod connection, the ramp of foam, which, by the way, is about this large, this piece of foam. It's about this big. And it, just like if you threw a styrofoam glass out the window of your car, which I'm not encouraging you to do, but for science, of course, it gets caught up in the flow. It got caught up in the flow. So even though the space shuttle was going at about 1,600 miles an hour at the time, the piece of foam struck at about 500 miles an hour. It hadn't been fully decelerated or accelerated, depending on how you view it, to local airspeed, and that's what struck, and it put a hole in the wing. So then 2 weeks later, during re-entry, air stagnated in this hole. And the intent of the being carbon-carbon, the reinforced carbon-carbon, is so that it could take really high temperatures. Now air is stagnating essentially directly on that aluminum spar, and it gets softer and softer. Remember, it needs to slow down from 17,500 miles an hour. It gets softer and softer until it starts to wobble, the wing, because it's melting. We get the burn through, and that's what we were seeing on the gauges. When gauges went offline, so we knew when the lines, the electrical lines had burned, and then the vehicle began to tumble and broke up. So that's the debris that was subsequently seen over Dallas, where the breakup happened. And then the pieces ended up in Texas and Louisiana and some in the Gulf. So that's the physical cause. of the loss of the orbiter, and it's a strong conclusion. I mean, that's certainly what happened. So I want to point out a little bit about what you saw, even though I skipped over some of the technical slides, but we had this three-pronged approach. We did experiments, we did large-scale numerical simulations, we also did analytical theory, theoretical modeling. When all of these come together, you can draw strong conclusions that you understand the mechanics, that you understand the physics. Okay, well now I'd like to say a little bit about the organizational cause. So we did not work on the organizational cause. Okay, so don't get confused there. So essentially what I'm reporting is hearsay, right? Meaning I read the report, I later came to know some of the people, but we were just in our impact group at Southwest Research involved in looking at the foam strike on the wing. That's what we did. At the same time, NASA was doing, or the Columbia Accident Investigation Board was doing an investigation. So how did decisions get made before and during flight that led to the accident? So this was their organizational cause. The organizational causes of this accident are rooted in the Space Shuttle program's history and culture, including the original compromises that were required to gain approval for the shuttle program, subsequent years of resource constraints, fluctuating priorities, schedule pressures, mischaracterization of the shuttle as operational rather than developmental, and lack of an agreed upon national vision. Cultural traits and organizational practices detrimental to safety and reliability were allowed to develop, including, and I'm going to point out some things about this next one, reliance on past success as a substitute for sound engineering practices. And they say such as testing to understand why systems were not performing in accordance with requirement specifications, organizational barriers which prevented effective communication of critical safety information and stifled professional differences of opinion, lack of integrated management across program elements, and the evolution of an informal chain of command and decision-making processes that operated outside the organizational rules. So there are a number of things. I mean, there's lots of things. They almost said throwing everything here, right? But let's talk about a couple of items that are, to me, and how we were involved, interesting. So I can't emphasize enough that the people who designed the space shuttle were smart people. I mean, they were super smart people. That worked at North American Aviation, that worked on the X-15, that worked on the Lunar Command Module. I mean, they knew how to design high-speed aircraft and spacecraft. But they made a decision here which was, in hindsight, unfortunate. And that was the space shuttle. This was from the design guides. The space shuttle system, including the ground system, shall be designed to preclude the shedding of ice and or other debris from the shuttle elements during pre-launch and flight operations. External tank debris limits. No debris shall emanate from the critical zone of the external tank. This was the design. We're not going to have debris. The reality was different. They knew debris could be a problem. Their approach was to say, hey, we're just not going to have it. And, so that was part of the design, right? To design not to have it. But it turned out that was, well, I wouldn't say hard to do. That was impossible to do. There was debris on every single flight that came off the external tanks. And this is an example showing, this is from the Columbia Accident Investigation Report, because the Columbia Accident Investigation Board directed NASA to go back and compile all your data from every flight. We want to know what happened. And you'll see these are bars, and sometimes the number of tiles damaged are, in the one case, the really high bar, over 250 tiles were damaged by debris. So there was debris every flight. So this is an example of their statement of reliance on success rather than sound engineering judgment. So yes, the shuttle was flying okay, but every time it came back, it was by observation, not in compliance with the design and operating guides. But it was like, okay, but it's operating okay, right? Clearly it works. So we're gonna keep flying. You'll see some little red triangles here. Those red triangles are the 7 times where they could tell, and the only way you could tell was by video on orbit, which occasionally was taken if the separation of the external tank occurred in sunlight. of how many times did either all or part of that left bipod ramp separate. It had happened 7 times on observables 72 flights. In other words, that piece of foam was either in part or all coming off 10% of the time. Interestingly, you might think Space Shuttle looks symmetric to me. It's not exactly symmetric, and the external tank is not exactly symmetric. There's no instance of the right bipod ramp of foam ever separating. It's only the left one. And so this brings up, we have the statement that was in the report: history of failure becomes a memory of success, meaning we're not performing like we're supposed to perform, but hey, it worked. And then I did the quote from the senator from New York from years ago, where he wrote a report on the normalization of deviancy that was happening in the city, which was a different kind of deviancy. But here, people just got used to, we're not actually performing as we should, but we're okay with it. I will say, I have one positive aspect of that, from my opinion. So we lost 2 space shuttles in the operation of the space shuttle. And I've talked to one of the people who was on the phone with NASA for the Challenger accident saying, don't fly tomorrow, it's too cold for the O-rings. So that was a known issue. NASA chose to fly anyway, even though technical people were on the line from Brigham City, Utah, saying, do not fly, it is too cold for the O-rings. They flew anyway, and it was an O-ring failure that led to the accident. In this case, you may notice that we have two of these left bipod ramp separations. Well, excuse me. This one is the accident separation. We have the one bipod ramp that happened 2 flights before. Because of that, this left bipod was on the top 10 safety list, and it got a waiver for this flight. To me, though, the positive thing is we knew what the problems were with the vehicle. We maybe made bad decisions, but I actually think that's better than we have no idea why we lost a vehicle. So we knew there were challenges, but you choose to accept risk, and you choose to accept how much you're willing to take. One of the challenges is maybe you don't know what the risk actually is, right? So that's one of the things that was addressed in the return to flight program. And we did lots of work looking at the return to flight, trying to really understand the impact damage that could occur to the space shuttle so that flight managers would understand the risk. I think I'd like to say one other thing. This is all hearsay. It's in the report, but because I wasn't there, it's hearsay for me to repeat it, right? But if you read the report, it's in the report. If NASA knew about the foam strike, what happened during the flight, right? This is a valid question. So 2 days after launch, they set up a committee to try to understand, they're looking at the film footage they have of the ascent, and people say, it looks like there's a foam strike. They set up a committee then to look at it, and about 1 week into the flight, that committee met at Johnson Space Center to make their report. My understanding is it was standing room only out into the halls for a 7 a.m. report presentation. Their conclusion was, we don't understand the impact physics, so we need more information. So at that point, behind the scenes and overtly in front of the scenes, people started saying, we need more information. Unfortunately, the flight manager resisted that recommendation. So you might say, what's more information? More information would be to try to photograph the wings, right? And in fact, so people started working behind the scenes to get and there are people probably in this room who know more about it than me, to get certain agencies to take pictures anyway in the orbiter, on orbit. It would require support from the astronauts to position the vehicle right for those optical assets to be able to see the wing well enough to see if there's a problem. And the flight manager called off all those efforts. So that information was never gathered that might have made a difference. Now it's fair to say, and this is in the report also, if it made, because initially the flight people in charge said, oh, it would have made no difference. And if it makes no difference, it literally makes no moral difference, right? It doesn't matter if you couldn't have made any difference. So one of the things the Columbia Accident Investigation Board tasked people with was putting together, could it have made a difference? And the feeling was that yes, in fact, the next orbiter in line could have been working round the clock, could have been allowed to fly within 3 weeks. We could have asked the astronauts to eat less. And then we could have launched the other orbiter, understanding with the same risk that just led to the loss of Columbia, but with 2 pilots and no other crew, could have gone up and taken the 7 crew members from Columbia and come back down, assuming nothing went wrong. So there was something that potentially could happen if they'd known that there was a hole in the wing. Okay, we did the return to flight. We were involved in these critical math models, as they were said, to understand what the risk was so that future shuttle flight managers would have an understanding of what decisions am I making and what is the risk based on the impact threat, which is what we were involved in. Again, it's the external tank. Stuff comes off the external tank. Foam, it never stopped coming off. So that's not the end story. You might say, so they finally solved that foam coming off problem. No, we never solved that. We got the foam pieces to be smaller. We removed that left bipod ramp piece of foam and replaced it with a heater so that ice wouldn't form on that steel fitting. But stuff still came off every flight. This is an example. We looked at the debris transport, the damage then to tiles, to leading edge. This is a burn through of the leading edge panel, which we did in the labs, right? So this didn't occur on flight. So then a little over 2 years later, it led to the return flight by Discovery. I had hoped to be there, but instead I was in Pascagoula, Mississippi for the program review for the DDX destroyer, which is now the DDG-1000 Zumwalt, the next generation destroyer. A conference room that would shortly be wiped out by a hurricane. But I actually adjusted the agenda for that meeting and inserted, we will watch the launch. So we put up on the video screen and we watched the launch as a group, and then we went back to the review program for the destroyer. So I don't know if you can hear this, but if you're quiet, this is an audio recording essentially from the wing of the return to flight that had the first one, STS-114, and you know, the lady who was Eileen Collins, who was commander of this mission, lives in San Antonio now. Yeah, her husband got a job here, and they came to San Antonio. But this, if you can hear, we'll see if it'll play, and you can hear it. So each one of those little clips is foam striking the wing during ascent. So we never solved that problem. And you might say, well, you just make the wing stronger. That makes it heavier. So the effort was to make sure the pieces of foam that came off were smaller so that there still wouldn't be a threat to the wing. This is that flight's damage sketch afterwards. Was there damage to the vehicle? Yes. These are little tags for damaged tiles. Those are some of us looking at doing the inspection. And yeah, so every flight still had damage, but it was less to the vehicle. And we felt we had a better understanding of the risk. For some of the flights, we actually did impact tests during the flight because of stuff that was seen during ascent to really quantify the damage. So we did that right here in Southwest Research. We did impacts to reflect those tests. And those are just some samples. And there were lots of subsequent flights, even more than this. It went all the way through. The final flight was in 2011, STS-135, which was the 135th. They resynced them, 135th flight of the Space Shuttle system. I was able to take my wife and daughters out to the one before. NASA gave us nice VIP seats out at Kennedy to watch that launch, and so that was very nice. Again, if there's something technical you walk away from, we do experiments, we do large-scale numerical simulations on big computers, and we do theoretical modeling, which has cool equations. And when all of those come together, we have strong conclusions about our results. Thank you.
Could you go over those equations one more time?
We can derive them if you like.
Thank you, thank you. Do we have any questions? We've got people with mics on the other side. No questions? Oh, we've got a question over here. We have a question over here. Well, Mike, I'll let you ask a question while you...
Were there backup shuttles available on all the subsequent flights?
I don't know about all, but certainly for the first one, there was backup flight available. So I don't know if, as again, I don't know for all of them, but certainly for that first one.
For backup for 125, that Hubble Space Telescope.
Hold on a second, please.
Yeah, there was one backup mission post Columbia, and it was 125. It was that Hubble Space Telescope satellite repair that they did for that.
Yeah, so a difference to that one was, at the time, NASA canceled the Hubble Space Telescope repair missions because for the other flights, the statement was, we're just always going to go to the space station, so we can park them at the space station for an extended period if necessary before the next shuttle would come to pick them up. But the Hubble Space Telescope is not close to the space station, and it's not in an orbit close to the space station. So to go on a mission there, there's no going to you have to get there shortly. So that was the difference. Yeah.
Got a question over here, please?
How much of the shuttle was recovered that you could use for actual?
So this is based on the report again, right? I never was in the hangar with all the pieces laid out, but I believe they recovered about 40% of the mass of the vehicle.
Any other questions? One more, okay.
Yeah, Dr. Walker, is there any chance that that piece of foam was had condensation coming off of the external tank that made it more like a piece of ice or not?
So the insulating foam is a closed cell foam, so we don't think there was ice in the foam. We do know that sometimes ice forms outside the foam and sticks to the foam. And so for sure, every flight after Columbia, high resolution pictures were being taken, and one of them was delayed because of observed ice forming on external foam. The feeling though is that, based on the work we did, that amount of damage could be caused by foam without ice. So it's unless the ice was a mechanism for the separation, that's not really relevant. Right?
Okay, first of all, I want to thank you again. John, would you come up here, please? Please. Anna.
Yes, sir.
Thank you for putting me in touch with John, who put me in touch with James, who put me in touch. No. Anyway, I want to give each one of y'all a challenge coin from the ARC.
Thank you.
We appreciate it. Ladies and gentlemen, thank you for attending. They'll stay after if you have some questions. And this meeting is adjourned. Thank you.